Hello everyone. If you are here, this is the Physical 2 midterm review session. We're going to be going over each of the labs in sequential order, and at the end of each lab, if you have any questions, we'll look into the chat and answer them. You can ask your questions at any time and we'll just get to them at the end of the section. Does anybody have any questions about the midterm before we start?
Is it going to be memorization, or you have to identify things?
The midterm is going to be all multiples choice and a few matching answers. So you won't have to identify rocks with pictures per se, but there will be a couple of questions asking to match rocks to their definitions, and the definitions are going to be in your midterm review document, which is under the I think it's week 7 or 8 module that has the midterm, and if by chance we didn't get it published, let us know. So yeah, the definitions will be in there, and we're also going to be going over some rock definitions as well. Any other questions?
I think that answers the other question of what should we be expecting on this test. So I think that answers that as well.
Alright. So first we're going to get into lab 1, which is map essentials. So if you guys remember way back to lab 1, maps should have all of these things as a part of it to be considered a good map. We aren't going to go necessarily in depth to all of the things, but a key thing to remember is that all of these are map essentials, like the directional reference, the legend or key, the source, the date, the name of the cartographer, projection, scale, and a locational reference. All of these are map essentials. We're going to go a little bit more in depth into the legend and key, because from the lab results it seems like some people had a little trouble with that. So a legend or key is essentially what it says. It places a key into a corner of a map, and it describes different symbols or colors or pictures that you might find on the map, and lets you know what they are, because maps typically take a big space and squish them down into a little piece of paper. So symbols and graphics and colors have become kind of a shorthand to let people know what things mean on a map. This is just a few examples that you will find in a map legend. You can find things such as a school building, a church, a rock quarry, airport, roads, swamp area, lakes, woods, and etc. There's a bunch of different types of symbols or graphics that can be found in a legend or a key, but this is just a few examples. Next, we're going to be going over projection. So, as we all know, the Earth is round and it is kind of a sphere shape. So, most maps are presented on a flat piece of paper. So, when you squish a sphere onto a flat plane, types of distortion happen. And projections often solve certain types of distortion. And we're going to be going over a few types of distortion that you can find on a map. The first example is distortion in direction. So, as you can see on this picture right here, airplanes are kind of traveling in a curve. Some people might think, why don't they just travel a straight line from point A to point B? Well, That's because on a map, a straight line might seem like the most efficient route, but a lot of the times you're actually traveling in a curve because, of course, the Earth is a sphere. The next type of distortion is distortion in area. So sometimes when you place the Earth on a map, some areas get enlarged. A great example of this is Greenland. Greenland is not nearly as large as it is presented on many maps. Greenland is probably about 50% that size. So sometimes when you put things on a map, they often stretch and become larger. And this is not to be confused with the next section, distortion in shape. So distortion in shape is kind of similar to distortion in area, except this really messes up the areas. So distortion in shape, as you can see from this picture, it stretches and elongates and generally just messes up different features on a map. As you saw with area before, it just made things seem bigger. It didn't really mess them up too much besides not knowing what its actual size is. Distortion in shape actually makes this almost unreadable. Next, we're going to be talking about the types of scales you can find on a map. So, scales compare and convert the distances measured on a map into real-world distances on the Earth. So, we're going to be going over the representative fraction. So, the representative fraction, which is also just shorthand to RF, is a mathematical equation of sorts to convert distances from measuring on a map to real world distances. So it's relatively simple. So let's say you have a map and you measure 1 inch on that map. So if you measure an inch on the map, you know you have an inch. So you look at the RF, and let's say, for example, the RF is 1 to 24,000. That means that 1 of a unit is equal to 24,000 of that same unit in real-world space. So let's go back. We have an inch that we measured. That means that in real-world space, our inch is equal to 24,000 inches. So essentially, let's say you measure 5 inches on a map, and that map is from a representative fraction of 1 to 10,000. That means 5 inches would be 50,000 real-world inches on that map. And that leads into the next thing we're going to be talking about, unit conversion. So in your midterm review document, it gives you this exact chart right here in order to convert different units of measurement into others. So we have English to English, English to metric, metric to metric, and then metric to English. All right. Double check this real quick. Let's make this a bit smaller. There we go. So let's say that you have a map laid out in front of you, and its scale is 1 to 75,000, right? So you measure 10 inches on that map. How far is this in real life in miles? So this is doing a couple of different things. First, we're converting the inches that we got into real world inches. So we have 10 inches, and the RF is 75,000. So essentially we just multiply 10 by 75,000 and we get 750,000. But then we want to convert that into miles. So if we go back to our handy dandy chart back here, we can see that there are 63,360 inches in 1 mile. So that means all we have to do to convert it into miles is divide 750,000 by 63,360, and then you can get your miles, which is 11 miles, at almost 12, but it's 11.83 miles. You can kind of do this in the inverse as well. So let's say you know the distance from like point A to point B is 11.83 miles in real life, but you some reason want to go back and know how many inches on the map that is. So you can do that by essentially inversing the formula. All right, before we get into lab 2, does anybody have any questions on lab 1?
There are no questions in the chat.
All right. All right, so in lab 2, we're going to be getting into topographic maps. So there are going to be a couple of questions on the midterm asking you to find different latitudes and longitudes on the map. So let's see. So let's see, for example, we want to know the lat and long of, let's say, Delhi. So what we're going to do is we're just going to estimate this because we can't really get down to the fine details with this type of map. So we know that Delhi is right around in here. So first let's get the latitude. So if we go over here, we know that Delhi is between 20 and 40, almost exactly. So probably a good estimate of the latitude that Delhi is at is around 30 degrees north. And then when we want the longitude, we know that it's almost right up against the 80 degrees east. So, let's just click the pointer. Yeah. We know it's right up against 80 degrees east. So it'd probably be a safe assumption that Delhi would be at like 30 degrees north and probably around 75 degrees east. And we can do something, we can do a similar thing or something way off. Let's go Cape Town. So we want to get the latitude again, and this time we're in the southern hemisphere and we're almost right up close to 40 degrees south. So a safe estimate there would be around 35 degrees south, and we know we're right up against this line right here, and we can see that these lines are at about 20 degree intervals. So a safe assumption would be that it is 20 degrees east. So around 35 degrees south, 20 degrees east. And you all probably remember the Jacksonville quadrangles. There's going to be a few questions about that as well. And so some of you had a little bit of trouble being able to estimate the latitude and longitude of an area on the quadrangles. So we're going to go through that now. So let's say we are going to let's get the lat and long of, I think this is Sulphur Springs. So we can see right down here, we have, or maybe not. Trust me, there's like a 50-minute symbol right here in the bottom left. And as we go on up, we know that up here is 52 minutes. So we know that, or actually 52 minutes and 30 seconds. So we know that somewhere between here there are 2 minutes and 30 seconds. So if we kind of just estimate, like right here, this is probably around 30-ish seconds away based on mentally like dividing this up. So we would know that this area is probably 50 minutes and 30 seconds from this 50. So we know our degrees are always going to be 33 degrees. So we know that the latitude of this area is around 33 degrees, 50 minutes, and 30 seconds. And now we want to get the longitude. So we know that right here we have 85 degrees, 52 minutes, and 30 seconds. And over here we have 50 minutes. So again, we know that there's 2 minutes and 30 seconds somewhere between here. And if we use the same estimation from before, this is probably about 30 seconds away here. And don't try to like stress your mind over getting things exact. This is just estimation. So as long as you guys are in the ballpark, you'll be able to find the correct answer on the midterm. And if what you're doing is like not in the ballpark at all, you just have to redo finding the lat and long. But anyways, so we know that this is probably around 85 degrees and 52 minutes. So our full latitude and longitude will be lat 33 degrees, 50 minutes and 30 seconds north, and the longitude will be 85 degrees and 52 minutes west. All right. Before Ms. Heron takes over Lab 3, does anybody have any questions about Lab 2?
There are no new current questions in the chat.
All right, well, Ms. Heron is going to take over the igneous and sedimentary rock labs, and I'll be back for the volcano lab.
All right. Hello, everyone. Thank you, Mr. Ferguson, for those. All right, so we're going to get into Lab 3 on the igneous rocks. And so I want you to remember igneous rocks are formed by the cooling and solidification of magma. They are classified on 2 factors, and that's texture and composition, okay? And so I really want y'all to pay attention to what textures are versus what composition is. And for the sake of this class, we'll get in a little more on those compositions in a moment. But right now we're going to talk about the textures. We have a phaneritic texture, apenitic texture, glassy, porphyritic, and pyroclastic. Some of the main things with this that I really want you to pay attention to is intrusive and extrusive. Intrusive being it was in the earth when it started to solidify. and extrusive mean it was outside of the Earth's surface as it began to solidify, okay? So some of these rocks that you see are going to be similar of each other, but one was in the Earth, whereas the other got shot out of the Earth, either the volcano or slow cracks or whatever. And then the glassy texture that we'll go over, let me see, I'll pull you up some examples here in a minute. But the glassy texture that we're going to get on is a real fast. It's extrusive and it gets up out of there, out of a volcano really fast, cools really quickly. And one of the key things I want you to note with this texture is if you are being asked how it is cooling, texture is where you need to look on this, okay? And all right, and then your porphyritic, you have crystals that are encased in a ground mass, and then the pyroclastic, they're produced by a gassy, violent volcanic eruption, which we also call pyroclastic flows and things, and so they'll have vesicles and they'll be really light. And so we'll start off with a gabbro, and I'm going to get you an example here as well. And this is an extrusive igneous rock, meaning it was in the ground, and that forms from the result of slow cooling of magma inside a volcano. And so this is a gabbro. Hang on, let me get over here. Can you see?
It'll take a second to load.
All right.
Yeah, probably a little closer
You see it all right?
though. Take it a little closer.
The camera's up towards the
Camera's
top.
on top, yeah.
Oh, well, maybe that's why.
Okay, yeah, that was good.
Okay, sorry, trying to find the camera, guys. Getting used to this one. All right, so this is a gabbro rock, all right? And so this is intrusive.
Oh, don't put it above it.
Oh, what? Huh?
Sorry, yeah, hold it side. Yeah, that, yeah.
Like hold it in front on top of it.
Yeah.
Like, you can't see behind it.
On top in front of it, right here.
Oh, don't-
Sorry, guys, getting used to this.
About here-ish, you can see.
Ah. Okay. All right, so hopefully y'all can see this better. I have photos that are uploaded as well so that you can get a better idea. But this gabbro here, again, this is an intrusive igneous rock. Notice the darker color with the crystals here. And this means that it's slowly cooled. And with it being darker, this is a felsic. I'll get in a little more with that, but it's a felsic composition as well. And it does have some lighter crystals within it. All right? And this here, can we still see? Am I good? All right, this is basalt that I have here. And basalt is the equivalent, the extrusive or outside of the volcano or above the Earth's surface of gabbro. And notice how it's got a dark composition. And you can't really see many crystals on this. All right, I'll get into basalt a little more here in a moment. All right, so granite. Grab your granite. And I've been showing y'all my students. I've actually shown a diorite. So I want to clarify to my students on the granite that I have here. And so here is the granite. If y'all can see this okay?
Yeah, right there.
All right, so the granite, this is a felsic rock. So notice this light composition here. And it's has large phaneritic crystals. So you can see the large crystals within this. And it's composed of clear quartz, black minerals, and some relatively light colored feldspar, which is where you're getting some of these different colors within this. All right. And so we did say the basalt that I showed you a while ago, which was this guy here. Just going to quickly let you see him again. The basalt. All right, he is a mafic rock, meaning he's darker in color, aphanitic and extrusive. has small dark crystals that are not always easily seen. All right, so the porphyritic rhyolite is an extrusive felsic and has salt and pepper spots. So you can see the salt and pepper spots here. That's in the porphyritic rhyolite. And there's black crystals that are embedded in that. If you look close, you might can see some of those crystals embedded within. And this is the extrusive equivalent of the granite that you were shown. So this is the granite, which cools beneath the ground. It's intrusive. And this is your porphyritic rhyolite, which is extrusive. All right? All right, so next we're going to get into obsidian. And as you can see, obsidian has a really glassy texture and it's really smooth. And this is because of how quickly it cooled. When it's an extrusive rock, so when it is shot out, it cools very quickly, sometimes by water, mostly by water, isn't it? Okay, yeah, I was thinking. So you'll see this a lot along like Hawaii when it's hitting, coming off the sides of the island there and is directly hitting water. And that's obsidian. And obsidian, for the sake, I noticed we had a little bit of confusion within the book on a summary table. And so what I want you to know with this is it is felsic, okay? It's extremely felsic. All right, and then pumice. This is one we touched on in our class, but we didn't go too intense with this. And so I really want to take a moment and let y'all see it. The pumice is a power clastic, which means it is it comes from a very high flowing volcano. And it's low in density, and it's covered in vesicles and light in color. And so if you can see this pumice here, it's really light. This low density, this is really light. And if you look close, you can see the vesicles within. And vesicles just meaning it's like little tubules, kind of veins within the rock, I guess you could say, or porous. And so there you go. We just hit the obsidian, so let's get that. All right, and did we know the gabbro? Okay, I've shown y'all the gabbro. Just to go over that, these slides may have duplicated because I.
Oh, you have a question?
Okay.
Would pumice be extrusive?
Pumice would be extrusive, yes. Yes, because it's coming out of a pyroclastic volcano, often seen with your, like, is it the cinder cones that I'm thinking of? The composite volcanoes, where you get a really high amount of magma that comes out at a really strong force. And is there any other questions?
Currently no.
All right. And I thought I hit on the gabbro. I did hit on the gabbro. All right, so we're going to skip that. All right, so we're going to jump into sedimentary rocks. All right, so the formation of sedimentary rocks. All right, so it's created through four distinctive steps, okay, guys? And so we have weathering of the rocks to produce the sediments, small fragments of rock or dissolved ions. And one of the things I want you to note with the sediment is, the sedimentary rocks, is that it is the breakdown of the igneous rocks that we've discussed. So the igneous rocks are what's formed by the magmas and everything, and then it's further broken down and that's where we get our sedimentary rocks. And there's a couple different ways of breaking down. You've got the weathered, and then transportation. So the weathering of the rock produces sediments, small fragments of rock, or dissolved ions. And then the transportation of these sediments to a new area can also kind of change that a little bit. Deposition of the sediments in this area. And lithification of these sediments. And lith meaning rock, so lithification meaning it turns into a rock. And so these are some of the important sedimentary rocks that we have listed, but we're going to go a little bit further into that. This will be on your review as well. All right, so the weathering. So we have two different types of weathering, guys. We've got mechanical and we have chemical. All right, and so mechanical is typically, it is the breaking, it's the fracturing of rocks. And this can be done through biological activity or temperature changes like a freeze-thaw, where it freezes and then it thaws and it freezes and it thaws, and over time this is just breaking the rock apart. Biological activity that you might see is tree roots busting through the rock and breaking it apart, or animals burrowing through it. That's a few things that you might see with mechanical. And then there's a variety of others. And then you also have weathering that happens as a result of exposure to the atmosphere, mostly water or oxygen. And all of these, like I said, are considered mechanical or chemical. So I'm going to jump into the transportation that we discussed as well. And so you've got transportation of clastic fragments of weathered rock. And so small fragments of the rock produced by physical weathering may be transported by a variety of natural processes, such as wind, glaciers, gravity, waves on a beach, and most importantly, running water. We see a lot of that in Alabama. And something I want to touch on with the glacier, just to throw it out there, but glacier till is something that is a word in geography that we love to use, in geology. So running water is responsible for the transportation of the enormous quantities of sediment that later forms most clastic sedimentary rocks. And so we'll jump into that a little more. One thing I do want you to remember is the size of the particle that can be moved in proportion to the velocity of the water. So slow moving water has a low energy. And so this low energy means it can only pick up some of your smaller types of particles. And when we talk about those particles, we discussed this earlier. It's not in this slide, but we went over gravel. Gravel being 2 millimeters or more. And then sand being 0.02, am I right on that? To 2 millimeters? I don't have those numbers in front of me. Sand, 0.02 to 2 millimeters?
Yeah, I think so.
Plus 2 millimeters to 0.05, silts 0.05, 0.002.
So it goes from 2 to 0.00 to 0.05. Okay.
Yes.
All right. So we go from 2 millimeters with gravel, and then the next step down is sand, which goes from 2 millimeters to 0.05 millimeters, and then the next step down is silt, and this is where you can kind of feel it. Kind of feels like flour. If you've ever baked flour, it's kind of silky, but you can't really feel each individual particle like you could with sand or even gravel. And it is 0.02 to 0.05. Excuse me, 0.002 to 0.05. And then you would get down to our smallest particle, which is clay. And that is 0.002 and below. So just think of that when you're thinking of how this is moving through. Like I said, the slow moving, low energy is going to move those smaller particles. So you're going to see more silts and clays being moved with that. Whereas fast moving, high energy, it takes relatively large particles. And so your gravels and your sands can be carried easier at that. And once it gets into suspension, it really starts moving fast. And so these relationships kind of give us a clue as to where these rocks were created. And this is just more examples. As the rocks fragment, these fragments are transported, they change in shape. And so you can see on the slide that the ones over to the left, they become nice and rounded. And then the one over to the right, which is your conglomerate, it ends up lithifying to form a new rock. And so, let's see. We'll jump into that a little bit. Well, let's go ahead. So this is the conglomerate through here. Notice the particles, the larger gravels that's within it, and then the smaller particles that have helped solidify this through, or lithification, okay, through lithification. And this is a clastic rock. All right, so the transportation of ions. So the one a while ago was the fragments of rocks. This one is of ions, so this is smaller. And so this is chemical weathering that destroys the mineral structures, and some of these ions will be released and be taken into the solution by water. Remember that water is a really great solvent, so it can just about dissolve anything over time. These dissolved ions contained in a river are called solution loads. We often test this through TSS or TDS, which is total suspended solids or total dissolved solids. And since this load consists of individual ions, typically water still appears to be clear, but with these tests you can find that there are small particles within it. And the solution can often be tasted. You can often taste the difference in the waters of these. Pure water is almost tasteless, while dissolved ions will give the water its flavor. And the deposition of sediments, which is the next one to know. The deposit of sediments happens when the transportation stops. All right, so we transported either ions or fragments. It was weathered first, then we transported, and now the deposition is how these sediments are stopping their transportation. So when the water stops running, either from hitting a large river or hitting the ocean or hitting a lake, and so you've lost that high energy flow or that slow moving flow, and all of a sudden it's kind of come to a stop, you have different things that start falling out of the solution, and they start making their way to the bottom. So we're no longer in solution of the water. We've now dropped down to the bottom of the waterway that it's located in. And so this changes, this can cause larger particles to be deposited, followed by the smaller ones. And I mean, if you think about that, if you have something small and light in your hand versus something heavy and large in your hand, and you drop it at the same time, the heavy and larger is going to hit the ground before the lighter and smaller will. All right, so the lithification of clastic fragments. Once these particles have been transported to their new area, they must be transformed, a collection of loose sediment into a new or solid rock. And this process is called lithification, hence that conglomerate I showed a while ago. Lithification is a combination of two processes. You have compaction. And compaction occurs when sediments are squeezed together, and cementation occurs when particles are glued together by other minerals. So here you can see the conglomerate is cementation, and the red sandstone is cementation, and the shell is compaction. All right, so So again, there's your conglomeration. All right. And that is cementation. So these rocks have been cemented together. And it's harder to see. Can you see this okay here? It's harder to see this, but this red sandstone has small particles within it, which is also cemented together. All right? And then the shell that we have here is compaction. So this compaction means it had pressure and compacted it together rather than being cemented together, if you can see that really good. All right. All right, so the lithification of dissolved ions.
We have a question, Dana.
Yes,
They're asking if you can define conglomerate again.
define conglomerates again.
Yes.
All right, so the conglomerate is a clastic rock that is relatively round due to traveling great distances, and it consists mostly of gravel with sand, silt, or clay mixed in. And it is, we'll go back. So if you look at the conglomerate, it is cementation, and it has larger rocks that are cemented together by smaller ions, or smaller particles. Does that answer the question? Is that
Yeah, I think so.
okay? All right, so yes, the lithification of dissolved ions. Ions dissolved in the water can be undissolved and turned into new minerals. All right, so this process is called precipitation, and it can happen organically or inorganically. All right, so inorganic precipitation is typically produced by evaporation. So as water is evaporated, once we've slowed down that the transportation and we've gotten to that lake or ocean or wherever we are, and we've fallen out of solution and we've hit the bottom, then some of these places you get evaporation. A lot of times you'll see this in certain wetlands or in formal streams where it runs only certain times. And so as this water is evaporated, the remaining water cannot always keep the dissolved minerals. So these minerals join together to create a new mineral or crystals, which then drop to the bottom of the body of water. So chert, do we have chert in here? I've got it on here. So chert is a really good example of an inorganic precipitation. And then organic precipitation results from biological activities. All right, so many organisms have the ability to remove dissolved ions from solution, and they use the ions to build hard structures such as shell, teeth, and bones. We see this a lot with oceanic creatures, and even in freshwater areas you can see this. And so I'll take you to the next slide. So this gets us into the limestone and the chert. All right, and there's that photo.
Sorry? I stole it myself. I don't think I had church in.
All right, so I don't know if I've got any chert in here, but this here is a dolomite limestone. You can see this here, and you can notice the darker areas from the iron within it, and then this is a different type of limestone. I'll give you that answer on that one in just one moment. But you can see, sometimes you can probably see it better up there. You can see the shells and some of the other things that are encased within it. So yeah, the shell limestone is composed almost entirely of broken pieces of seashell and other marine organisms. All right, and the dolomitic limestone, which is the little gray one that I showed you, it forms inorganically and no traces of shell fragments or the fossils, but you can see some darker colors within it. And then the chert, I believe we hit on that. On the other, but again, that's an organic precipitation as well. All right, and then the classification, you've got the clastic and you've got chemical. So clastic are formed from fragments of other rocks. These are further classified by the size of these fragments. And then chemical rocks are formed by the precipitation of dissolved ions out of solution. These are further classified based on the types of minerals that they do contain. And so an example of a clastic would be a conglomerate. And like sandstone is primarily of sand, but contains a significant amount of clay. That's another clastic. Shell was clastic, right?
Shale,
Yeah, all right, yeah, I think
Oh,
so.
shit.
Yeah. And then the chemical rocks that we discussed, the bituminous coal. Is it? Huh?
And chert.
And chert, okay, yeah. So the chert was also a chemical rock. And then we're gonna get into the bituminous coal here in just a moment. And this bituminous coal consists of sediments that are bits and pieces of wood and other plants, plant parts that are accumulated in stagnant water. So, can you see this all right? This bituminous coal. And so there's a few pieces. Like I said, you've got pieces of wood and other plant parts accumulated because it is sitting in stagnant water here. And like we said, with it falling out, that organic precipitation. All right, and I'm gonna let Mr. Ferguson jump back in. He's gonna talk to you guys a little more on volcanoes. If anybody's got any questions real quick, I'll be happy to answer what I can. Don't see any questions?
There are no questions in the chat.
Okay.
All right, so we're going to get into volcanoes now. So before we talk about the types of volcanoes or what type of magma they have, first let's get into why volcanoes erupt. So to put it simply, is pressure. But to go more in depth, magma often has dissolved gases within the molten rock. So eventually, when pressure becomes too great, an eruption occurs. So normally you have magma sitting down like inside of a volcano, and it also depends on the thickness of the lava, like the type of lava it is, if it's more viscous or less so. But pressure starts to build, and then the lava can't really contain its gases anymore, and an eruption occurs. Eruptions often come from, or are composed of, ash and water vapor. Alright, so there are going to be three different types of lava that we're going to be talking about, which are the the Pahoehoe, and pillow lava. So the first one is So this lava is primarily basaltic in composition, and they are typically what create like rocks that are higher in iron and lower in silica. So, and with that property, it can be assumed that these are more viscous than other types of magma. So this lava is really thick and it flows really slowly. And you can compare the consistency of this lava to like jello or liquid glue. Out of the three we're talking about, this lava is lower in temperature. It's from 1,000 degrees Celsius to 1,100. Next is the Pahoehoe. This lava is low in viscosity. So this lava can be compared to the consistency of water or oil, and this flows really quickly and really easily. And these lavas, their temperature tends to be around like 1,100 to 1,200 Celsius. Sometimes it's not only the composition that makes lava more or less viscous, it's also the temperature. So depending on like if it's made of like or if it's like and primarily basaltic, or if it's like Pahoehoe and it's more or supposed to be more viscous, depending on the temperature, it's going to be more or less so. But these classifications mostly hit things on the head. Next we have pillow lava. So this lava is essentially lava that erupts from the earth from underwater. So sometimes pillow lava, since it is being instantly cooled, it can have things such as obsidian inside of it. But a lot of the time the texture of this lava is pillowy because as it erupts, its shell like breaks and comes back together through the quick cooling, and it gives it a pillowy and rounded appearance, and that's how it gets its name. Next we're going to be talking about the different types of volcanoes. So the first one we're going to get into is the cinder cone. So the cinder cone is what you would think of if you think of the stereotypical volcano. A cinder cone has a central vent that is normally pointed upwards, and it is characterized by its bowl-shaped crater. So how the crater forms normally, it is when it erupts, rock fragments fall and collect around the vent, and it keeps building up and building up until it gets pretty tall. But these are one of the smaller volcanoes that we're talking about, and they're only around 1,000 to 1,500 feet tall. Next we have the composite volcanoes. So these volcanoes are one of the largest volcanoes on Earth. We have, for example, Mount St. Helens in Washington and Mount Fuji in Japan. These are some well-known examples of composite volcanoes. These volcanoes are also known as stratovolcanoes because they're so tall they reach into the stratosphere. These volcanoes, when they form, they are really symmetrical and extremely steep. These volcanoes are similar to cinder cones where they have a central vent, but unlike cinder cones, they also have fissures and vents that form like on the sides of the volcanoes that help magma move through. The last volcano we're going to be talking about is the shield volcano. These volcanoes are some of the largest volcanoes in our known solar system. For example, we have the Olympus Mons, which is on Mars, and this is the largest shield volcano in our solar system, and it is at around 69,000 feet tall. Some well-known shield volcanoes that are located here on Earth are the Mauna Kea in Hawaii, and it is considered one of the largest mountains, but because it starts below sea level, it is not considered the tallest mountain. So the Mauna Kea is around 33,000 feet tall, and it starts below sea level. Whereas something like Mount Everest, it starts above sea level, so that's why it's considered one of our tallest. So the lava flow is essentially how these volcanoes become so big. So lava keeps building up as it erupts, and most of the time these eruptions aren't very violent, so it just kind of oozes out of the top of the shield volcano, and more layers of solidified lava build up, and it keeps growing until the volcano becomes dormant. Sometimes these volcanoes can be 3 to 4 miles across. Alright, that's it for the midterm review. Does anybody have any questions about volcanoes?
There are no new questions in chat.
Alright, does anybody who might have joined late have any questions about the midterm? I'll give you a minute to ask.
Let them know I found some stuff that will be added to the midterm. So if they have already downloaded the midterm that is there, I have found some more stuff on sedimentary rocks that needs to be added.
If you guys didn't hear Ms. Herron, she's going to add more things to the review thing, or the review document that is on Canvas. So if you've already downloaded it, be prepared to download it again because she's adding more things about sedimentary rocks. Any questions about the midterm yet?
Still no new questions in chat?
Alright, well, if anybody happens to have any questions about the topics covered or about the midterm, you can always email us, message us on Canvas, and that's it for the midterm review. Everyone have a nice day.